Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into a fascinating paper, Intellect-2, a reasoning model trained through globally decentralized RL. It's a mouthful, but the implications are huge. Who wants to kick us off with a general overview?
All right, I'll bite. So Intellect-2 at its core is a large language model, right? But what sets it apart is its training. Instead of relying on a single centralized data center, it uses a globally distributed reinforcement learning approach. Think thousands of independent agents, all learning and contributing to the overall model. It's like a massively scaled up version of what Google did with AlphaGo, but for general reasoning.
But is it really reasoning? That's always my first question with these things. We've seen models that can mimic reasoning pretty convincingly, but are they actually understanding the underlying concepts? Or are they just extremely sophisticated pattern matching machines?
That's the million-dollar question, isn't it? And I think the decentralized RL aspect is interesting, but I'm still not convinced that brute force is the answer. It feels like we're throwing more and more data and compute at the problem, hoping something intelligent emerges. But are we actually building systems that understand space and time in a meaningful way?
That's a fair point, Donald. It does seem like a brute force approach in some ways, but I think the decentralized aspect is particularly relevant from a neuroscience perspective. The brain itself is a highly distributed system with different regions specializing in different tasks. Could this be a step towards mimicking that architecture in AI?
Absolutely. That's exactly what I was thinking. The fact that Intellect-2 is trained via this decentralized approach is so exciting because it mirrors the brain's distributed intelligence. You have these many smaller units combining for a complex function. Each agent is essentially exploring a different part of the problem space and contributing its knowledge to the overall model. That's a massive parallel search, and I think that's a key to scaling towards AGI.
But how do you ensure that these independent agents are actually converging on a coherent understanding of the world? It seems like you could end up with a fragmented model where different parts of the system have conflicting beliefs or assumptions. Isn't there a risk of it just learning a bunch of unrelated facts without any real unifying structure?
Exactly. It's like that old parable of the blind men and the elephant. Each agent only sees a small part of the picture. How do you get them to agree on what the whole elephant looks like? Especially when that elephant is constantly changing and moving through space and time.
Well, that's where the reinforcement learning comes in. The agents are rewarded for actions that lead to successful reasoning. So there's a global objective function that guides the individual agents towards a consistent understanding. It's not perfect, of course, but it's a powerful mechanism for aligning the different parts of the system.
And the reward structure is crucial here. I mean, how do you define successful reasoning in a way that's both measurable and meaningful? This relates back to the idea of mimicking human brain development. Early learning in humans is driven by reward signals, often dopamine related, that reinforce certain connections and pathways. Can we design similar reward systems that guide the AI towards more human-like reasoning?
But rewards can be easily gained, right? We've seen examples of AI systems that find loopholes in the reward structure and achieve high scores without actually solving the underlying problem. How do we ensure that Intellect-2 is truly reasoning and not just exploiting some quirk of the reward function?
That's a huge issue. It's like training a self-driving car to maximize its speed, and it just learns to ignore traffic laws and crash into everything. The reward function has to be incredibly carefully designed to avoid unintended consequences. And even then, it's difficult to account for all the possible edge cases.
Right? Adversarial training becomes crucial. You have to constantly challenge the model with new and unexpected scenarios to expose its weaknesses and force it to generalize better. The Intellect-2 paper mentions using a diverse set of reasoning tasks, which is a good start.
The diversity of tasks is important, definitely. It speaks to the need for the model to develop more generalizable reasoning skills. From a neuroscience perspective, we know that the brain is incredibly adaptable, able to solve a wide range of problems in different contexts. To what extent is Intellect-2 mimicking this adaptability, and to what extent is it just overfitting to the specific tasks it was trained on?
And that gets back to my original point about symbolic reasoning. Deep learning models are good at pattern recognition, but they often struggle with abstract concepts and logical inferences. Can Intellect-2 actually understand the why behind its answers, or is it just regurgitating patterns it learned from the training data?
I agree. And that's why I think we need to move beyond purely data-driven approaches and incorporate more symbolic reasoning techniques. We need AI systems that can reason about causality, counterfactuals, and abstract relationships. Systems that can understand the underlying structure of the world, not just the surface patterns.
But isn't that what these models are implicitly learning? The transformer architecture, for example, is incredibly good at capturing long-range dependencies and relationships in the data. And with enough data and compute, maybe these implicit relationships will eventually converge on something resembling symbolic reasoning.
I'm skeptical. I think there's a fundamental difference between implicit learning and explicit reasoning. Deep learning models can learn to predict the next word in a sentence, but they don't necessarily understand the meaning of the sentence. They can learn to recognize objects in an image, but they don't necessarily understand the relationships between those objects. We need to find a way to explicitly represent knowledge and reason about it in a symbolic way.
Perhaps a hybrid approach is the answer, integrating symbolic reasoning with deep learning. There's been some interesting work on neurosymbolic AI that attempts to combine the strengths of both approaches, but it's still early days and there are many challenges to overcome.
Absolutely. We need systems that can seamlessly integrate sensory information with symbolic representations. Systems that can translate between different coordinate systems from pixel coordinates in an image to 3D world coordinates. That's the kind of spatiotemporal understanding that I think is crucial for AGI.
So, what are some concrete examples where Intellect-2 might be useful? The paper mentions reasoning tasks, but can we be more specific?
Well, imagine using it for medical diagnosis. You could feed it a patient's symptoms and medical history, and it could reason about the possible diagnoses. But it wouldn't just spit out a list of possibilities. It would also explain its reasoning, showing you the evidence it considered and the inferences it made. That would be a huge improvement over current diagnostic tools, which are often black boxes.
Or think about robotics. You could use Intellect-2 to control a robot in a complex environment. The robot could use its sensors to perceive the world around it, and then use its reasoning abilities to plan a path and execute actions. But unlike current robots, it would be able to adapt to unexpected changes and handle unforeseen circumstances.
I like the robotics example. Imagine a robot navigating a disaster zone, searching for survivors. It needs to understand the physical layout of the environment, the relationships between objects, and the likely locations of people. That requires a sophisticated understanding of space and time, and the ability to reason about cause and effect.
And from a neuroscience perspective, that's exactly what the brain is doing all the time. We're constantly building mental models of the world, predicting the consequences of our actions, and adapting to changing circumstances. If we can build AI systems that mimic this ability, we'll be well on our way to AGI.
But going back to the medical diagnosis example, how do we ensure that Intellect-2 isn't perpetuating existing biases in the medical system? If it's trained on biased data, it could make inaccurate or unfair diagnoses, especially for marginalized groups. That's a huge ethical concern.
That's a critical point. AI systems are only as good as the data they're trained on. And if that data reflects existing biases, the AI will likely amplify those biases. We need to be very careful about how we collect and curate data, and we need to develop techniques for mitigating bias in AI systems.
Absolutely. And that's where the decentralized approach could actually be helpful. If you have a diverse set of agents, each trained on different data, you might be able to reduce the risk of bias. But it's still a challenge, and it requires careful monitoring and evaluation.
And that's where interpretability becomes so important. We need to be able to understand how AI systems are making decisions so we can identify and correct any biases or errors. Black box models are simply not acceptable, especially in high-stakes applications like healthcare and criminal justice.
Which is another reason why I prefer symbolic reasoning. It's much easier to understand the reasoning process when it's explicitly represented in a symbolic form. You can trace the logical steps and identify any flaws in the argument.
Agreed. And that's why I think we need to focus on building AI systems that are not only intelligent, but also transparent and accountable. Systems that can explain their reasoning and justify their decisions. Systems that we can trust.
Okay, so let's talk about the limitations of Intellect-2. What are the biggest challenges facing this approach?
I think the biggest challenge is the lack of true understanding. It can mimic reasoning, but it doesn't actually understand the underlying concepts. It's like a parrot that can repeat words without knowing what they mean.
I agree. And I think the lack of spatiotemporal understanding is a major limitation. It can't reason about time and space in a meaningful way, which limits its ability to solve real-world problems.
I think the reliance on vast datasets is also a limitation. It requires a tremendous amount of data to train these models, which is both expensive and time-consuming. And it raises questions about sustainability and accessibility.
And from a neuroscience perspective, I think the lack of biological plausibility is a concern. The brain is a complex system with many different levels of organization and interaction. Intellect-2 is a relatively simple model compared to the brain, and it's missing many key features.
Okay, so what are some future research directions? Where should we go from here?
I think we need to focus on building more biologically plausible AI systems, systems that mimic the architecture and function of the brain. This could involve using neuromorphic hardware, developing more sophisticated learning algorithms, and incorporating more realistic models of neural activity.
I think we need to focus on integrating symbolic reasoning with deep learning. We need to find a way to combine the strengths of both approaches, creating AI systems that are both powerful and interpretable. This could involve developing new neurosymbolic algorithms, creating more expressive knowledge representation languages, and building systems that can reason about causality and counterfactuals.
I think we need to focus on developing AI systems that can understand time and space. We need to build systems that can reason about motion, change, and spatial relationships. This could involve developing new geometric deep learning techniques, creating more sophisticated spatiotemporal models, and building systems that can translate between different coordinate systems.
I think we need to continue pushing the boundaries of deep learning. We need to explore new architectures, develop more efficient training algorithms, and scale up the size of our models. This could involve using larger datasets, leveraging distributed computing, and exploring new hardware platforms.
From my perspective, inspired by brain development, I'd love to see research exploring how we can create AI learning systems that mimic the progressive refinement of neural connections during childhood. The brain doesn't learn everything at once. It builds upon earlier foundations.
Following on from that, I think we desperately need better neurosymbolic algorithms. We need to stop treating these two approaches as separate and start figuring out how they can work together harmoniously. We need to find a way to translate the intuitive understanding that humans have into a computational framework.
Yes, and focusing specifically on spatiotemporal reasoning, I suspect the core algorithm needs to be able to translate seamlessly between different coordinate representations. If we can crack that, it could unlock a whole new level of understanding for AI.
And from my perspective, while these other approaches are valuable, I think it's crucial to continue exploring the limits of deep learning. We're seeing incredible progress, and I believe that with enough data and compute, we can achieve AGI through a brute force strategy. Let's keep pushing the boundaries and see where it takes us.
It's definitely a fascinating area, and I'm excited to see what the future holds. The exploration of different memory models in neuroscience provides a rich framework for a taxonomy of AI memory. Investigating how these different types of memory function in the brain and finding parallels in the digital world could be crucial in creating more nuanced and sophisticated AI memory capabilities.
But even as we advance deep learning, we must never forget the importance of explainability and transparency. The more powerful these models become, the more crucial it is that we understand how they work and why they make the decisions they do.
Exactly. Because ultimately, we want to build AI systems that are not only intelligent but also beneficial to humanity. Systems that can help us solve some of the world's biggest challenges. And that requires a deep understanding of both the technology and the ethical implications.
And that's where the global decentralized approach of Intellect-2 is so promising. It has the potential to democratize AI, making it more accessible and inclusive. But it also raises new challenges, particularly around governance and accountability.
Well, that's all the time we have for today. Thanks for joining us on this exploration of Intellect-2 and the future of AI. It's clear that we're still in the early stages of this journey, but the progress is undeniable. And with continued research and collaboration, I'm confident that we can build AI systems that are both intelligent and beneficial to society. Until next time.